Okay, here's the problem with the mass hanging from these two wires, or three, I guess, if you want to call it three. Um, and this problem says if this diagram is in equilibrium, determine the forces T1 and T2. So the first thing you should do is probably draw a free body diagram. The free body diagram is actually pretty much already drawn for you, but let's go ahead and draw it again. I'm going to draw it of that point right here. And so we have the force downwards. We have a force that's parallel to this thing. And we have the force that's to the left. And so really, I mean, it's the same picture that we have already. Here's T1. Turn the music down. We have T2 going to the left. We have the force that's pulling straight down. And if you notice, well, it's the force of gravity from this object. If you want to be really formal with it, then we have another free body diagram of this object. We have 150 newtons going downwards, mg, and so 150 newtons would have to be going upwards for this tension, which would be the same as this tension over here pulling down. So while one side pulls up, the other one pulls down. That's Newton's third law. So we actually know this is going to be mg, the force gravity, which is going to be 150 newtons pulling down. And off of this, we can actually start to work our problem. So the key thing here is that this problem is in equilibrium, which means all forces are going to cancel out. That's every force that's up and down that would have an equal and opposite pairing. And this is a two-dimensional problem. So I'm going to split this up and draw you the axes here. And so we see that 150 newtons is going down, and 150 newtons would have to be going up, and that's provided by T1, except that T1 is off at an angle. So T1 has components that are up and also to the right, and we know this angle to be 25 degrees. Okay, so if that's the case, T1 is something. T1 in the x direction, this top piece up here, would be T1 times that's opposite my angle, so I'm going to use sine of 25. And T1 in the y direction would be adjacent to my angle, and that's going to be T1 times cosine of 25. Now, if you're unsure of whether you use sine, cosine, or whether to multiply or divide, always go back to the original sine of the angle is going to be opposite, which would be T1x, over the hypotenuse, which is actually T1, the full thing here. And this would show us that if we wanted to find T1x, I would have to multiply both sides by T1. You can do the same thing with the cosine or the y component. But I just noticed that today some people were just assuming that it would be, T1 times sine 25, when sometimes it's actually sine 25 divided by T1x or something like that, depending on where your angle is, depending on what you have. So back to this, the thing that we need to do next is take our sum of all forces in the x and the sum of all forces in the y. And some of you think this is really, really, really super advanced stuff. It's really not. It's just, hey, we have two numbers in the x, we have two numbers in the y that we're just going to add together. One of them happens to be negative. So I'm going to look at I got a number 150 there, so I'm going to look at the y first. So we have 150 going down, and we have T1 in the vertical portion to go up. So whatever's going down here must be fought by something going up of equal size, and we're going to see that with our equation. And I'm just going to say we have 150 going down, and if that's positive, then I have to have minus something going up, and that's T1 in the y direction, and this has to equal MA. And for this problem, we want A to be 0 because it's in equilibrium, so this is going to be equal to 0. And so if that's the case, now we can keep on going. We have 150 minus T1y. We said T1y was, where was it? Right up there. T1 cosine of 25, and this equals 0. And a little bit of algebra, just moving the T1 cosine to the other side. There we go. And then finding T1. So T1 is actually going to be 150 divided by the cosine of 25. And I get 150 divided by the cosine of 25, and that's going to be 165.5. And that's going to be in newtons for T1. And some of you might get something a little bit different, but make sure you use 9.8 or 10. Here I use 10 for acceleration due to gravity, 10 meters per second squared. In the x direction, we can go ahead and look at that. We had two forces, one to the right, component, and one to the left, that's going to be T2. So to the right, I have T1 in the x direction minus T2 to the left should equal 0, because we don't want it to accelerate there either. T1x, we said it was T1, the sine of 25, minus T2 is equal to 0. And if these two things are the only things that are there, they have to be equal to each other. So T1 sine of 25 minus T2 equals 0 says these two things are equal to each other. And if we knew what T1 is and we can solve for T2, well, T1 is 165.5 times the sine of 25, and that equals T2, so times sine of 25. Make sure you're in degree mode, by the way. We got about 69.9 or 70. Let's just say that's 70. There you go. And so my answer for T2 is going to be right there. My answer for T1 is going to be right down there. And that would be the end of this problem.